this is Tiago from Coderversity, and in today's video I'm going to be teaching you asynchronous programming. You will learn why use asynchronous programming, asynchronous programming basics, task-based asynchronous pattern, exception handling in asynchronous programming, and synchronization context and UI thread. For that we will be using C# and .NET. So what are we waiting for? Let's dive in. Asynchronous programming is very important in building responsive and efficient applications. In order for me to unwrap what asynchronous programming is, I need to tell you what is a main thread. In programming, the main thread refers to the initial thread of execution that is created when a program starts. It is responsible for running the core part of the program. In most applications, this thread executes the main logic, handling the program's control flow. So, in asynchronous programming, it allows you to run tasks in background, so non-blocking, while the main thread can continue doing the other work. Scenarios where async is crucial. For example, while waiting for HTTP requests, for example, fetching data from an API, or a file input and output operations, for example, reading large files from disk. Another example would be database queries, when you can retrieve data from an SQL database, for example. There are two very important terms that should be introduced, the async and the await. Async and await are keywords in .NET that enable writing asynchronous code. When the program pauses waiting for a task to finish, it causes delay in the entire app. This is a blockage. So, why use asynchronous programming? A synchronous method from fetching data from a web API can be written like this. Public string, and let's simulate that we are fetching data. Let me save this as a CS file. Example. And we will fetch data synchronously. So let's write var client equals a new HTTP client. We are creating here an HTTP client, and we are returning our string that will be get string async, let's say from this API, https api.example.com data. And to be synchronous and to block the main thread, we will put results so that the main thread doesn't go on while this result isn't retrieved. So this code blocks the main thread, like I said, because .result is a synchronous wait. The program has to wait for getStringAsync method to finish retrieving data before it can proceed, freezing the main thread, which could cause delays or UI freezing in desktop apps. What is the solution here? The solution is to introduce AsyncAwait as a way to avoid blocking by letting the program continue running while the data is being fetched in the background. So, for example, if we change the async and we retrieve a task, the task is retrieved every time we are doing asynchronous calls. So we keep the HTTP client, and this would be the response equals to await this response, and then we return it. Async and await are the foundational keywords for writing asynchronous code in .NET. Async marks a method as asynchronous and tells the compiler that the method contains code that could run asynchronously. And the await is used to pause the method execution until the awaited task is finished. But the main thread is not blocked. Other tasks can continue in the meantime. The await keyword does not block the thread. Instead, it pauses the method execution and gives control back to the calling thread, allowing it to continue with other work. Once the getString async call completes, the method resumes execution just as if it had been paused at that line. This pattern is highly efficient for input-output bound tasks, for example web requests, file reads, or database access. It is a common pitfall of using async void like this, for example, because you should avoid this for anything except for event handlers, as it prevents proper exception handling and doesn't return a task, making it harder to track errors. There is a pattern very useful that is called task-based asynchronous pattern, TAP, and task methods. So the task-based asynchronous pattern, TAP, is the modern way of handling async code in .NET. In TAP, asynchronous operations return a task or a task of the type T, for example, this, or any type, let's use T for generic, that you might want, representing a promise of future completion. You can await tasks, run them concurrently, and handle errors effectively. Important methods to know is the task.run that runs code on a separate thread, useful for CPU-bound work, the task.whenAll that waits for multiple tasks to complete in parallel, and tasks when any that waits for the first task to complete. So, for example, let's put like this, and let's change the method a bit. Let's call it fetch multiple data async. And then we write the first task for this method. That is, let's assume we have a client for an API already created, and we do string async. And we call the API https api.example.com data1, and let's do another task to retrieve data2. That will be called task2. And then we will do await task.when, not task1, the static method task.whenAll task1 and task2, and then we console.writeLine both tasks are completed. With this task.whenAll, both API calls are made simultaneously. This is much faster than making the two calls sequentially. This method is crucial when you need to perform multiple asynchronous operations concurrently, significantly improving application performance. Note that we don't have the awaits before each task, which would make it synchronous, but rather we put the two tasks to work and then we wait them all at the same time so that they can run in parallel, not blocking the main thread. Handling exceptions in async code works similarly to synchronous code with try-catch blocks. However, you need to be aware of unobserved task exception in some cases. Let's write an example. Safe fetch async. Let's leave one task, and let's involve this code within a try-catch. HTTP request exception EX. Let's format this. And console.writeLine request failed ex.message. And let's put the the string interpolation, and there we go. The exception is thrown here when this await resumes after the getStringAsync task fails. Without await, exceptions might not be caught unless the task is explicitly awaited. So let's imagine that we don't have here the await. The task runs in parallel with the main thread. So let's say that we await for this method, but not for getAstringAsync. The getAstringAsync can terminate after this code is awaited, so we might not get the exception. Always use await and in an async method to ensure proper execution, exception propagation. Now, let's understand a very important concept that is called ConfigureAwait. Let's write the code to explain that. So let's fetch data without deadlock. Let's remove here the try catch. Let's format. And then let's remove here the one. Let's call it data and dot configure await to false. And then let's say we have a method to process this data that we are retrieving from the API. So in this case, this code will continue on a background thread. ConfigureAwait to false here tells the runtime that you don't need to capture the synchronization context, for example, returning to the UI thread in a desktop app. Why use it? In a non-UI bound applications like ASP.NET Core or background services, returning to the same context is unnecessary and adds overhead. So, by using ConfigureAwait to false can improve performance, especially in libraries or backend services where there is no UI thread to return to. A common scenario is in an ASP.NET Core web app. If you don't use ConfigureAwait false, the continuation of an awaited task may cause unnecessary performance degradation by trying to get back to the original thread unnecessarily. In more detail, the synchronous context governs which thread asynchronous code continues on after waiting a task. In UI applications like WPF or WinForms, the UI thread handles user interactions. If asynchronous code resumes on a different thread, it may cause issues when updating UI elements, as UI operations can only be performed on the UI thread. So, as you can see, the UI and the backend, so the frontend and the backend, operate in two different threads. That's why the synchronization context is very important. For example, let's say we have here a task for button click async on the UI side. And then imagine that this is a front-end app. We await a task.delay of 1 second. This is in milliseconds, that's why I'm putting 1000. This simulates a non-UI bound operation like something in C#, so a database retrieval, for example. And then we do button.text equals to done. In UI apps, the continuation of an async method automatically happens on the UI thread by default. This ensures that UI elements, like the button, can be updated safely. Then we can use ConfigureAwait false in non-UI bound applications like we simulated here. That can be a task from backend. Let's simulate a request for, let's imagine we are doing here an API request like we did before, and this uses 1 second to be completed. And this avoids to returning to the UI thread where it's unnecessary and adds overhead. So, In conclusion, we saw what the sync and await was, what a task definition is, exception handling, ConfigureAwait, and the sync best practices. It is very important that you use asynchronous programming for building efficient, scalable, and responsive applications in .NET. In fact, I encourage you to explore further, apply these principles on your own projects, and continue learning more advanced topics like parallel programming or concurrency handling. And with that, we wrap up our tutorial on asynchronous programming. I hope you found this project helpful and that you learned something new along the way. If you followed along, congratulations on completing the project. Don't forget to like this video if you enjoyed it and consider subscribing to the channel for more programming tutorials and projects. If you have any questions, suggestions, or just want to share your own version of the project, drop a comment below. I would love to hear from you. Thanks for watching and happy coding. See you in the next video.